everyone. Welcome to the pre-lecture for Chapter 7. I'm Karle, one of the Stat 100 TAs, and today I'm going to be talking to you guys about regression. So in Chapter 6, we looked at predicting y values from x values using the SD line. And when we were making these predictions, we were assuming that we had a perfect correlation between our x and y variables, meaning that our correlation coefficient, or R, was equal to either 1 or -1. If you guys can remember, we did an example in the notes where we were looking to predict someone's weight from their height using the SD line. So again, we had that perfect correlation of 1 between weight and height. Now, this was a good prediction for people that are exactly as tall as they are heavy in comparison to the average. However, in real life, usually we don't have a perfect correlation. Usually there's people that are tall and skinny or shorter and heavier, so the SD line might not be the most accurate prediction. Now we're going to look at making predictions using the regression line rather than the SD line. And the regression line allows us to look at a graph of averages. In other words, for each x value, the regression line looks at the average of all the y values associated with that x value. So what I mean, looking at this visually, if we have this graph right here with height on our x-axis and weight on our y-axis, if we look at x equals 65, we can see that for our y values, there's kind of a football-shaped region around all of our y values. And the regression line takes the average of all of these y values for x equals 65, and that's how we get the regression line. So in other words, we use the regression line when we don't have a perfect correlation, when R is not equal to 1 or -1. It's somewhere in between. And this is usually the case. In real life, perfect correlations are hard to come by. And if we did happen to have a perfect correlation, our SD line and regression line would essentially be the same line. So the main difference between the SD line and the regression line is the slope. So let's look at how we draw both the SD line and the regression line, and if we can see that difference in slopes when we draw them. So for the SD line, remember, again, we're assuming that we have a perfect correlation. So our R is equal to 1. So if we have this point right here on our XY axis, if we increase 1 standard deviation in the x direction, for the SD line we have a perfect correlation. We're also going to increase 1 standard deviation in the y direction. So now this is our prediction, and this is how we're going to be able to draw our SD line. Now the regression line, remember, doesn't have that perfect correlation. Our R is not equal to 1. So let's do an example where our correlation coefficient is equal to 0.3. So now if we start at this same point and move 1 standard deviation in the x direction, instead of moving 1 standard deviation in the y direction, we're only going to go up 0.3 standard deviations in the y direction for the regression line to make our prediction. So here, as you can see, our regression line looks different than our SD line. Our regression line is not as steep. Our SD line and our regression line do look different. They have different slopes. And the SD line is steeper than our regression line. This is always the case. The SD line is always steeper. And what I mean by steeper is that if you think of these two lines as a slide, the SD line, or the steeper line, would take less time to go down. And if that's too confusing for you, you could always think that SD line, steeper, slide, all start with S. So SD line is the steeper line. So remember before, I said that the main difference between the regression line and the SD line are the slopes. So let's actually go ahead and calculate the slope for our SD line and then the slope for our regression line. So hopefully in algebra, everyone learned the formula for slope. So does anyone in the audience remember what that formula is?
I do.
Yes.
It's change in y over change in x.
Right, change in y over change in x. So first we're looking at the SD line. Here from our graph, we can see that our change in y is just 1 SDY. And our change in x is also just 1 SDX. So our slope, as you guys saw in chapter 6, is indeed SDY over SDX for the SD line. Now let's look at the regression line. Remember again, change in y over change in x. So now our change in y, it isn't just SD of y, it's 0.3 times our SD of y. So we have 0.3 times SDY for our change in y over, again, we have that same just 1 SD for the change in x. So now if we simplify this, we have 0.3 times the SD of y over the SD of x. But remember, our correlation coefficient isn't always going to be 0.3. This is just for this specific case. So can anybody think of a way to write this in a more general form that we can apply to other problems? Yes, Steve?
With r?
Right. R is what we represent our correlation coefficient by. So our slope for the regression line is actually r times our SD of y over SD of x. So as you can see, our two slopes are different, and before we said that the SD line is always steeper, and it makes sense because r, our correlation coefficient, is always going to be less than 1. So this line is always going to be flatter, the regression line. Now let's look at an example where we actually use the regression line to make a prediction. So in this example, we're going to look at predicting someone's hourly wage from their age. And these two variables are correlated. They have a correlation coefficient of 0.75. However, they're not perfectly correlated. They don't have that correlation of 1. So before we begin, would anyone like to come up and point out which of these two lines is the SD line and which one is the regression line? Yes.
You said the SD line is always steeper, so that would have to be this one. And then that would have to be the regression line.
Right, that's exactly right. The SD line is always steeper. So this is the SD line, and the brown line is our regression line, and that's what we're going to use here to make the prediction. So we want to predict someone's hourly wage for a person that is 25 years old. And we're given both the average and the standard deviation for age and hourly wage. So our first step is that we want to find the z-score for our age. We can't just compare age and hourly wage like they are right now because age is measured in years and hourly wage is measured in dollars. We need that common measuring stick of a z-score to be able to make our comparison. So, does anyone remember what the formula for the z-score is? No one? Okay. Well, the formula for the z-score is value minus average over the standard deviation. So now, if we have someone that's 25 years old, we're going to find their z-score by just plugging in our value, which is 25, the average for age. Well, we're given that. We know that's 21 years. And the SD for age, we also know is 2 years. So when we figure this out, we end up getting a z-score of 2. Now, back when we were using the SD line to make predictions, we would have said, okay, we have a z-score of 2 for age. That means we have a z-score of 2 for hourly wage. However, with the regression line, remember, our correlation coefficient is not 1. Instead, it's 0.75. So, if someone is 2 standard deviations away from the mean, which is what a z-score of 2 means for age, then we need to know the z-score for hourly wage, and we're going to multiply our z-score for age by that relationship, our R, 0.75, to get our new z-score for hourly wage. We need to multiply our z-score by a correlation coefficient so that we make sure we're taking into account that relationship between age and hourly wage. So our new z-score is 1.5. We get that from doing 2 times 0.75. So now we have our new z-score for hourly wage, and we want to get an actual value for hourly wage. So z-score, what does that mean? Our z-score means that we are, in this case, 1.5 standard deviations away from the average. So let's start out at the average for hourly wage. As we can see right here, that's 16. And then we're 1.5 standard deviations away. So we're going to add 1.5 times our standard deviation, which is 3. And when solving this, we get that our prediction for someone who's 25 years old for hourly wage is going to be $20.50.